The first concept we talked about last meeting was Lagrangian polynomials. In this Lagrangian polynomials, we can find the value of f, but there are some disadvantages or drawbacks or problems regarding this function, this method. An important one is by increasing the number of points, finding interpolation became very complicated and even inefficient in some cases. Another important drawbacks of this method, for example, Lagrangian polynomials, is that when a new point is inserted in this table, for example, the point number 4, x4 and f4, we should solve or find the function from the beginning, and this is the main drawbacks of these methods. Here we are going to talk about another important method called divided differences. In this method, finding a function became much computationally efficient, and also if we insert a new point in the table, we can use the last computations as well and find the suitable function as an interpolated function. We assume that we have the values of f at this point, x0. The value of f at this point is f0. The value of f at x1 is f1, and as follows. As you can see, we assume that our polynomial function is as this equation, for example, or in this case, as this function Pnx, polynomial of degree n, a0 plus x minus x0 multiplied by a1 plus as follows. And we introduce some important divided difference. For example, the divided difference between the first 2 points, x0, f0, and x1, f1 is this division. We showed that by f bracket x0, x1 equals this division, f1 minus f0 divided by x1 minus x0. At the this is the divided difference between f and x. The divided difference between this, the next 2 points. The first 2 points was x0 and x1. The next 2 points, x1 and x2, is in the second division. And we can define the divided difference of 3 points, x0, x1, and x2. The last division or the last equation, معادلة الآخر, in the last row of this slide. f x0, x1, and x2 equals f x1 and x2 minus f x0 and x1 divided by x2 minus x0, where f is defined in the previous equations and previous division. We can also define a single argument fxs, bracket fxs, just as a value of fs. The value of divided difference of xs and xt is ft minus fs divided by xt minus xs. And in general, the divided difference between n plus 1 point, x0, x1, and xn is equals the divided difference between the first endpoint minus the divided difference between the second endpoint, x1, x2, xn minus x0, x1, xn minus 1. The second endpoint, the divided difference of second endpoint minus the divided difference of the first endpoint divided by xn minus the last x minus the first x, the initial x. This is our definitions of divided difference in the last and the previous and this slide, and we can compute this or calculate these values or these divided differences in the table, as here we have the first two columns of this table given to us, and we can compute the third, fourth, and other columns of this table. For example, the divided difference of the first 2 points, x0, f0, and x1, f1 is f bracket x0 and x1, close the bracket. The second 2 points, we have in this table 5 points, x0, x1, x2, x3, and x4, and the value of f at this point. Regarding these 5 points, we get 4 divided differences. The divided difference between x0 and x1, x1 and x2, x2 and x3, x3 and x4. We have here 4 divided difference of first degree, and we can calculate the 3 divided difference between 3 points, x0, x1, and x2, and vice versa. You can see how we can compute this value is very easy, just division between f at these 2 points and divided by the difference of x. For example, here in the next slide, we have 5 points, xi 3.2, 2.7, 1, 4.8, and 5.6. And the value of f, you can see in the second column of this table. And by dividing the difference between 22 minus 17.8 divided by the difference between 3.2 and 2.7, we get 8.400 as the first divided difference between these 2 points. The divided difference between the second 2 points or second pair of points is computed very easily as 2.11, 6.34, and 16.75. We compute the fourth or calculate the fourth column of this table by dividing the difference between these two value, the first two value of the third column, and 3.2 divided by 3.2 minus 1.0, or y. For example, 8.4 minus 2.1 is equals 6.3 divided by 3.2 minus 2.7. We get 4.5, and we get these values, 2 point, and the other values as here. Remember that these values can be computed by this equation. And we can find the other degree of differences, divided differences, in the fifth and sixth columns of this table. And after that, easily computing the values or entries of this table, we can very easily rewrite our interpolated polynomial. At the first, we assume that we want to interpolate a polynomial of degree 3. And we can use this value, the first value of the second column, 22 plus 8.4 multiplied by x minus 3.2 plus the first value in the fourth column multiplied by x minus 3.2 as the last term, also with the x minus 2.7 plus this value minus 0.528 at this parenthesis, and this is the, we no longer need the last columns because we up to find the interpolation of degree 3. If you want to find the interpolation of the degree 4, we can use the last point, for example, x 5.6 and 51.7, and we can compute the differences as here. And the solution, P4x equals Assalamu alaikum. Degree 4, or P4x equals P3x plus the value of divided difference, the last value of the first value of the last column of this table, multiplied the parentheses x minus 3.2, x minus 2.7, x minus 1.0, x minus 4.8. This value is just added to the P3x. And in general, P4x is equals to these polynomials. An important feature of this method is that we can insert a new point. For example, if you want to the first 4 points, you can easily get P3x as follows. If you insert the last point, for example, xi equals 5.6, and the value of is this value, 51.7, we simply calculate the last value in each columns. This value, this value, this value, and this. And we can improve our interpolation polynomials by simply adding this divided difference multiplied by parentheses, the three last parentheses, and just a new parenthesis, x minus 4.8. This method really covers the problems of the last method, Lagrangian polynomials, and can be used, actually used widely in different approaches. Let me show this book. In this page of book, we can see, for example, if you want to polynomial of degree 0, we want to just we need just 1 point. A linear interpolation, we want 2 points, x0 and x1. 3 point, the interpolated function as this, endpoint, the interpolated function as this function, these polynomials. And it is very clear that the value of interpolation at point xi is equals fi, as we have this by just simply substituting x by xi. We can easily get the value of Pn as fi. And there is some algorithms. Let's examine the divided difference for polynomials. For example, we have these polynomials, and we by this we can compute the value of f at 1, 2, 3, 4, 5, 6 points. At point xi, the value of fi really follows this equation or this function. For example, when we substitute x by 1, we can easily get 2 minus 1 plus 1 minus 1 is equals 1. In the second row of this table, we can see the value of xi at point x equals 1 is 1, and the value of f is at the other points is computed by using this function. And we want to interpolate, reinterpolate, for example, the function f by these values of f, and we expected to get the same function. The first interpolation is first divide the difference in the third columns, the second divide the difference in the next columns, and vice versa. We can see in the last two columns we have the value of divided differences are equals 0, and this has a reason. There is a reason for that, because to interpolate a function of degree 3 or polynomial of degree 3, we just need 4 points. No extra point is needed, and we can use just the first 4 points, and we get 3 differences at the third columns, 2 differences, and the fourth columns, and 1 divided differences in fifth column of this table is equals to another column is equals to 0. If we substitute other points or insert other points to this table, and the result become the same, and we no longer need extra points for interpolation. Observe that the third divided differences are all the same, 2, 2, 2. And we can take advantage of this fact by not using differences beyond the column where the values are essentially constant. Because when the values are constant, 2, 2, 2, the difference easily became all 0. This gives us an important feature of interpolation. Now we want to discuss the errors of interpolation. For example, suppose that we have a real function f, and we interpolate the value of f by n plus 1 point, x0, x1, x2, xn minus 1, and xn. The error or ex is as the right side of this equation. This has a mathematical background, but you only need to know this equation suppose that we have a function f, fx equals x powered with 2, e minus x divided by 2x on 2. We have the first and the second columns generated by this function, the second columns, and the divided differences in the next columns as these values. And we discuss the errors in this table. For example, if we have we use the interpolation function of degree 1, degree 2, degree 3. We get different interpolated values in the next or second column. And in the third columns, we have actual errors, the difference between interpolated value and exact value of this function f at these points, and the value of the differentiation of degree n plus 1, the maximum amount of fn plus 1, or differentiation of order of n plus 1, and the minimum value for each interpolation, and upper bound and lower bound value of the function, as here this upper bound and lower bound is easily get by using this equation and substituting the maximum and the minimum value of fn plus 1 and fn plus 1, the differentiation of f of order n plus 1, maximum value of that and minimum value. If we use this value in this equation, we can easily get the upper and lower bound of this function. In most cases of interpolation, the function of f is unknown. Very seldom or rarely we can interpolate a known function. In cases of examination of different methods of interpolation, or we can use we interpolate a noun function, but here we assume that we want to estimate or interpolate an unknown function fx. Occasionally, almost always, when dealing with the experimental data, the function is unknown. For example, when you forecast the weather, the real function of weather is unknown. We interpolate the weather condition for the next day or next week just by interpolation. Still, there is a way to estimate the error of interpolation. This is because the n or the divided differences is itself an approximation of f and x, or differentiation of f of order n divided by n factorial. This term you can see in Taylor expansion or Taylor approximation of a function, as will be demonstrated in the fifth chapter. What this means is that the error of interpolation is given approximately by the value of the next term that would be added. This means E and X, or the error, is approximately equals the value of the next term that will be added to P and X. When you can see this error and the value of the next interpolation, for example, you can see P for X, the next term added to P3 is similar to errors, for example, with this value, because here we can see, for example, interpolation of degree 1, the error is 4.01, and the estimate from the next term rule is 0.2. The exact rule for degree 2 is as follows, and the estimate from the next rule. And there is a similarity between this, the next two, the second and the third columns of this table, which means this statement, or this term E and X is approximately equals the value of the next term that would be added to P and X. As you can see, the agreement is at least fair, which means there is a similarity, or this statement is not completely wrong, and it's right to some extent. If you have a question regarding this any question, otherwise we are going to the next concept. No question, and we continue, and we go to the next section, and we discuss some meaningful concept or feature of this way of interpolation. An important feature is that the order of points is not really important, and if we change the order, for example, we change the first point by the second point, we get the same function, same interpolation. And here we can see the computation or calculation of this table is upward, because we can see the value as this. uh, x0, x1, x2, x3, x4, we can index the points upwardly as this manner. The values of this table is same as this, but we order the arrangement of the points. For example, from x0, x1, x2, x3, x4, we use just the opposite, x4, x3, x2, x1, and x0, and we have this table. And the values of elements of this table, x0 is quite as this, and this is no matter when you change the order of the data, and the table is really not changed, and just the symbols we use are changed. In the previous examples, the data are not evenly spaced. For example, the difference between x0 and x1 may be different from the difference between the next 2 points. There are many cases, real case studies that the values of points are evenly spaced, and we can use the difference of function in order substituted by the divided difference. If the x values are evenly spaced, getting and interpolating polynomial is considerably simplified. Instead of using divided difference, ordinary differences, just difference between the values of function, are used. The differences in f values are not divided by the differences in x values. The delta symbol is used to write them, and for the table of n plus 1 or x in n plus 1 x fx pairs, differences up to the nth order can be computed. For example, we suppose that the table has entries indexed from 0 to n. First order differences are then written as a delta fi, this Latin symbol, that are computed as delta fi, the difference between fi plus 1 minus fi. The two consecutive value of f is subtracted from each other, and this difference is shown by delta fi, or simply del fi, for the index from 0 to n minus 1. Second order ordinary differences are shown by delta 2 fi, as this symbol are the differences of the first order differences. Delta 2 fi is differences between del fi plus 1 minus del fi, which is easily shown to be this value, equals to this value. You can see del 2 fi equals fi plus 2 minus 2 fi plus 1 plus fi. For these indexes, higher order differences are again the differences of the next order differences that can be computed from the original f values. Computing or calculating ordinary differences compared to divided differences became very easily and simplified, and we can simplify our computation and calculation even further in case of evenly spaced points. For example, when we compute the value of function at point 1, 2, 3, or 1 or point 2, point 3, point 4, point 5. These points are evenly spaced, and we can use the divided difference very easily. And interpolating polynomial of degree n can be written in terms of these ordinary differences with x evaluated as xs. For example, Pn xs equals f0 plus s, the s point s del f0 plus s s minus 1 2 factorial del 2f0 plus this, and this equation gives us interpolation and by computed ordinary differences of function f. We can see in the next table how we can easily compute the del f's, del 2f, del 3f from the table. For example, we have the x as the point 0, point 2, point 4, point 6, point 8, 1, 0, 1.0, and 1.2. It is obvious that the points are evenly spaced, or when we see the differences between consecutive points, these differences are remain the same when we cross these points. The value of f at these points is in the second column of this table. We just compute the differences between these consecutive points in the third columns. For example, 0.2 minus 0.0 equals 0.2. The difference between the third and the second point is this value. The fourth and the third is this value, and quite simple for other points. The fourth column is computed as same as the third columns from the data of the third columns. For example, when we compute the differences between the second and the first point, first values in these columns, we easily get this value, as follows. And other points can compute it very easily, and from this one, by this formula, we can easily find interpolated function. If you have any question, you can ask me or leave your comments. Also, the university system of Adobe Connect is activated, and you can download our meeting later from uh, the site, the site of the university easily. If you have any question, you can ask me. Uh, Let me explain further this example. In order to center the x values around x this point, we must use the four entries beginning for with x equals 0.4, then makes x0 this s as this value, inserting the proper values into expression from Newton and Grigori polynomial, we get this function f of this, the value at this point 0.4 here, and the second e del f in the third row as here, and the third value in this column, the next value in this row, excuse me, in this row, 0.096, and the interpolated value of f is equals to 0.893. And the function is actually for fx is tangent of x. This value is related to tangent of f, and the real value of tangent function at the point 0.73 is 0.895, which is quite close and to the interpolated value, and the error is 0.402. The next term rule, for example, if we use the next columns of this table, the error became this value, and our estimation became more precise or accurate. Let me experience this concept in the MATLAB my system gives me errors. random problem arise when we run in MATLAB. So maybe few minutes, maybe. If you have any question, MATLAB's diff commands gets the differences between the elements of a vector. So the columns of the above table are generated readily. We exhibit these as a rows to save space. For example, we have this raw vector here. And we compute the differences or binary differences of f by this command diff f. The answer is repeat your question, please. MATLAB is you can see my MATLAB is not mandatory, but in case of homeworks, you really need to program some of these questions in this MATLAB or other languages, for example, Python or Julia. But MATLAB is more used today, and for example, you need to be familiar with one of these softwares, maybe MATLAB or Python, not just MATLAB. One of them is quite needed. Let me this value f, this vector are you familiar with MATLAB? MATLAB, you can easily download this software and install on your computer, and commands for MATLAB is course. It's easy, and we can use this very easily. Next point. If you can compute this by this simple command, the answer is this value. We can, this is the third column of this table, del F. If we want to compute the fourth columns of this table, we can simply repeat this command, not for F, but for computed value or answer. In MATLAB, the answer is ANS. The answer is this vector. ANS equals this vector. You can simply expression or statement. Is incomplete or incorrect. The next columns we can use by repeating this for the last columns for A and S in this example, or in this book, the columns or the values of the F are computed or illustrated vertically. Here in MATLAB, in order to save space, we computed this horizontally or by row vector rather than column vector. You see the commands in MATLAB are simple, and you can use this very easily. If ANS for different value. Here's the relation between divided differences and function differences or binary differences. For example, f bracket xi until xi plus n equals del n fi divided by n factorial h powered with n. This is the relation between these two values, and you can see these differences in this interpolation. 2 factorial, del 2 factorial, del 3 factorial, which were quietly absent in this interpolation. For example, here, because the values, if we substitute f bracket x0 to xn by del nf n factorial, we require to simply get this interpolation. If you have any question, you can ask me. Here is a table of divided differences for this function, a function of degree 3, and which easily is obvious we need at most 4 point to interpolate this function. This, and other points are extra point, and in the fifth columns we get this constant value of divided differences, and computation of other columns are no longer required. You have a 10-minute rest, and we continue after our course after this 10 minutes to refresh your mind. Enjoy your 10-minute rest. Please repeat your question. I can understand what it says in some cases. In some points, there is a problems also with this method. Let me show you an example, and we want to introduce another method called spline curves. There are times when fitting and interpolating polynomial to data points is very difficult. Here is an example where we try to fit to a data pairs from a noun function. In most cases, we have a noun function, but here you have a noun function to examine the last method. Figure 3.1a is a plot of fx equals cosinus of x powered with 10 cosinus 10x on intervals -2, 2. It is a nice smooth curve, but has a pronounced maximum at x equals 0 and is near to x-axis for absolute value of x bigger than 1 became near to 0. This is the plot of f as cosinus of powered with 10x cosinus 10x. This is our function. Its plot is here, and we want to interpolate this function with a quadratic function or polynomial of degree 2. For example, at 3 point, -2, 2, and 0. The function is as here. You can see there is not a good interpolation, lots of differences, and let me use a polynomial of degree 4 for interpolation. Still it isn't a good fit or good interpolation of the original function. This continuous curve is p for x, and a continuous curve is the original curve of f. Example of polynomial of degree 6 or P66. You can see also there is differences. P8x became worse. And we want to introduce a spline curve and how a spline curve can really conquer this problem and efficiently approximate the values of function at other points. One might think that the solution to the problem would be to break up the intervals -2 until 2 into subintervals and fit separate polynomials to the function in these smaller intervals. Figure 3.2 is shows a much better fit if we use quadratic between x minus this and this value with the px equals 0 outside the intervals. In this case, we divided this interval into 3 subintervals. The first and the last intervals, we use p equivalent to 0 for approximation, and in the mid interval we use a quadratic function, and we can see quite good interpolation of the function of the original function. That is a better, and one could further improve to fit, but there are discontinuous in the slope. For example, the function is at this point and this point between the first interval and the second, and the point between the second interval and the last interval. There is a is not differentiable. The function is not differentiable, and one it is not a good answer. An answer to the dilemma is to use spline curves. Spline is a curve of degree 3. It borrows from the idea of a device used in drafting. The draftsman fits curves such as our example by bending a flexible rod to conform to the curve. The rod is held in place by placing weight on it. This device is better than using a French curve. For how the French curve is moved to conform is very subjective and is not effective where the curvature is great. Spline curves may be of varying degrees. Suppose that we have a set of n plus 1 points, x, I, y, I, and at these indexes 0, 1, 2 until n. A spline fit a set of n degree polynomials. We have a set of polynomials, not just one polynomial. We use a set of polynomials gix between each pair of points from xi to xi plus 1 the points at which the spline joins are called knots. Not the points at which splines are joined. If the polynomials are all of degree 1, we have a linear spline. You can see here we have a linear spline approximation of points. It's simply by connecting the dots, the adjacent dot in the surface or in the paper. As you can see, a slope are discontinuous where the segments join here at the dots. The slope or the function are not differentiable. As you can see, we have a different slope at this point. Before this point, we have a positive slope, and after this point, we have a negative slope, and this is not a good sign. Splines of degree greater than 1 do not have this problem. Most often, cubic splines or splines of degree 3 are used. And in this book, we concentrate our focus on cubic spline or spline of degree 3. In general, a spline of degree 3 is as this equation 3.9. Gix is aix minus xi power 3 plus bix minus xi power 2 plus cix minus xi plus di. This is a general formula for Gx or cubic spline at the point xi. We have between, for example, point xi and xi plus 1, this Gix and this curve. After that, we have another spline curve or Gi plus 1, and before that we have Gi minus 1x. We use a set of cubic spline to interpolate the function. We have another feature or property of this cubic spline. Thus, the cubic spline function we want is of the form Gx equals Gix on ith interval or interval xi plus 1. We have a function of different formula and meet these conditions. Gixi is yi for I0, I1, I and G n minus 1 xn equals yn. Gixi plus 1 equals Gi plus 1 xi plus 1 for this point. We have this condition for continuity. This condition ensures the continuous spline or function at the join points. The second one ensures the continuity of the slopes or differentiability of the function. And the last one is also ensure the slopes of degree 2 or is a twice differentiable function. This guarantee that our interpolation at these knots are twice differentiable. Equation 3.10 says that the cubic spline fit to each of the points. 3.10a is a continuous and it is a continuous in a slope and curvature. 3.10c and 3.10b. The first one is continuous in slope and continuous in curvature throughout the region spanned by points. We should apply this equation to ensure our interpolation. There are n plus 1 points. The number of intervals and number of GIX are n, thus there are 4 times n unknowns for each sub-intervals. We have 4 equations. As 4 the unknowns are AI, BI, CI, and DI. Unknowns is the parameters of these cubic splines AI, BI, CI, and DI. These values are unknown. Equation 10.3.10a immediately gives bi equals yi. Bi equals yi. We can easily get bi as values of yi for the value of function at I. The equation 3.10b gives yi plus 1 equals gi plus 1 xi equals this value plus yi IH 3i bi h2i ci hi plus yi. We substitute the differences between the x and xi plus 1 as a hi. AI hi power 3 bi hi2 cih plus y. This value says yi plus 1 equals this equation. We use hi, the difference between xi plus 1 minus xi, divide of the I interval. To relate the slope and curvature of the joining spline, we differentiate equation 3.9. And this gives us g prime I of x equals 3 ai x minus xi 2 plus these values, and the second derivation or second differentiation is this value, and observe that the second derivative of the cubic is linear, so g double prime of x is linear within this subinterval. The development is simplified if we write the equation in terms of the second derivative, that is, if we let si equals G double prime xi for I and Sn equals similar value, we get these values. Si equals 2bi, si plus 1 equals this one. And we can write bi is equals this and ai as these values. We substitute the relation for ai, bi, and bi given by these equations and solve for ci. We get ci as this equation. We now invoke to the condition that the slope of the two cubics that join at this point are the same. For example, we have this equation and then substitute x with xi, we get this y prime I equals ci, and also by substituting xi minus 1 to xi, we get this equation. Y prime I is equals to this value, and equating these, the substituting for A, B, C, and D, their relationships in terms of S and Y, we get this Y prime I, yi plus 1 minus yi divided by hy minus this division, which is equals to this equation. By simplifying this equation, we get this very important equation in this box, and the last part of that is divided differences between consecutive points xi minus xi plus 1. From this equation, we can see that from points 1 to points n minus 1, there are n plus 1 points. This gives n minus 1 equation relating the n plus 1 values of Si. We get two additional equations involving the first S and the last S, S0 and Sn, and we specify conditions pertaining to the end intervals of whole curve. To some extent, these end conditions are arbitrary, for alternative choices are often used. This is alternative choices. We can set S0 and Sn equals to 0. This makes the end cubics approach linearity at its extremities. This condition called natural spline. We have another three alternatives, but we are running out of the time, and we simply let it to the remained concept to the next meeting. We need to use additional class, and I want to ask you to give me a time in this before Thursday, and that we can have a class or have a meeting. But here we are running out of the time. And if you have any questions regarding this concept, you can easily ask me. Group is on the student to agree on a certain time and tell me for some extent. Not quite fluently, but I can speak to some extent. And طلاب يعني يريد بعد ساعة ما حالا من یکم بگم خانم زینب طالب حالا یکم حرفای من متوجه میشه.
السلام عليكم دكتور. سلام
علیکم.
خوبین دکتر؟
من شما رو به عنوان حالا نماینده انتخاب میکنم.
اوکی دکتر.
یه ساعتی رو تو این هفته قبل از پنجشنبه خب مشخص
بله
با هماهنگی بقیه حالا طلاب و دانشجوها که همه حالا موافق باشن، حالا اگه نباشن دقیقا 90% دانشجوها موافق باشن و بتونیم کلاس جبرانی حالا هفته قبل که تعطیل بود پنجشنبه ولی باید بذاریم یکی دو سه جلسه.
یعنی منظورتون پنجشنبه چند ساعت بگیریم درس؟ پنجشنبه خب خودمون درس داریم، کلاس داریم.
پنجشنبه آره قبلش
ها قبل پنجشنبه
یه ساعتی رو با هماهنگی بقیه.
ما چهارشنبه درس نداریم، کلاس نداریم چهارشنبه.
چهارشنبه اگه همه هماهنگن دیگه با خود شما به من بگید.
باشه چشم.
دانشجوها بگید که ساعتش رو دقیقاً مشخص کنید تو گروه، یکی دو روز قبلش تو گروه مشخص باشه.
باشه چشم.
که ما درس ادامه بدیم. من در خدمتتون هستم.
باشه ممنون، دستتون در نکنه. العفو أساتذة. يقول اليوم الأربعاء عندكم محاضرة؟ يقول نحتاج محاضرة قبل يوم الخميس خلال هذا الأسبوع. إيه والباقي إحنا ما عندنا الباقي، يعني ما عندهم جبر وما أعرف شنو. ها خول عاد. يلا خلينا نشوف كلكم أساتذة. ها يعني ها هي على يوم الأربعاء. ما قال، بس قال هذن المحاضرتين اللي راحت راح أسويهن محاضرة واحدة على يوم الأربعاء. شوفوا يا يوم من ذا الراحة مو الجايات، ما قال على الجايات.
يريد يكمل معناها المادة مالته، يريد ياخذ درس إضافي.
إيه يريد إيه مو يوم الخميس أو البارحة. أول البارحة كان مال هاي قال عطلة مال استشهاد فاطمة الزهراء. إيه هي المحاضرة راحت يريد يعوضها.
ما عندنا فراغ، قلينا ما عندنا فراغ.
نريد محاضرة تعويضية في يوم الأربعاء خلال هذا الأسبوع. أنتم كلكم موافق؟
كلكم موافقين؟ دي يسأل الستاف، منتظر جواب.
ما أعرف كيفكم.
ببخشید دکتر، دانشجوها میپرسن دیگه مثلا روز پنجشنبه آخرین کلاسمونه یا بازم کلاس دارین تا روز امتحان؟
کلاس داریم چون ما
داریم؟
ترسیم برگزار شده.
امتحانا اصلا کلا عقب افتاد. چقدر عقب افتاد؟
نمیدونم، شما بهتر در جریانید. من قرار شد عقب بندازن ولی دلیلش هنوز به من نگفتن. حالا شما اگه ساعتاشو دارید به من مشخص به من بگید که حالا من بدونم، چون قرار شد که به من بگن، حالا نمیدونم عوض کردن یا مشخص هنوز نکردن.
باشه. أتوقع حسب كلام الدكتور يقول هاي، يعني أتوقع بعد محاضراتكم عندنا، يعني ما خلص الكورس لأن امتحانات لسه حاليا ما محددين الوقت مالته شو وقت. حتى هو ما سألته على الفصل، هو قال حاليا محاضرات أكو أسبوعيا لحد ما تشوف الامتحان شو وقت. لا ما طبعا. بله دكتور.
دو تا فصل دیگه ما به جز این فصل داریم، البته فصل‌های
بعد
بعدی
فصلين.
ساده‌ترن. این فصل هم اگه نگاه کنیم نسبت به فصل‌های قبل ساده‌تر بود.
يقول بعد فصلين. اي رابع والخامس اتوقع، ويقول ذني شيء اسهل.
بهشون بگید که اگه ما امتحان هم مشخص شد نرسیدیم فصل رو تموم کنیم، میتونیم یه فصل رو فقط بگید، فقط پروژه براش مشخص کنیم.
بله متوجه نشم، میخواد صدا قطع بس میشه. صدا تو خیلی سألته كم مرة دزيت له، قلت له اعطينا نموذج أسئلة، قال لي ما يخاف أدزلكم. میگن یه نمونه از سال گذشته را اگه زحمت نمیشه برامون بفرستین تو گروه.
باشه.
ببینن چه مدلیه.
آره یادم بیاد که پیدا کنم براتون بفرستم.
ها ببخشید راست میگن دکتر، ما چیز نه بارکد و اینا شماره 4 در رقمو نداشتیم، فصل اول رو نبودیم اصلا، نمیدونیم مثلا کلاسمون از کجا شروع میشه.
حالا فصل اول میتونید از دوستاتون بپرسید.
خب بازم بهشون میگیم، اونام کسی بهمون جواب نداد. چند بار پرسیدیم ازشون هیچکی جوابمون نداد.
حالا بخونید، اگه مشکلی بود از خودم بگید بپرسن. تو گروه واتساپ که هستن، حالا میتونم سوال
باشه. يقول الفصل الأول داخل وشوفوا شنو الموضوع اللي ما هاي سألوني بيه، يعني دخلوا لي على الخاص وسألوني بيه. هسه على يوم الأربعاء ها هيك أوكي. ساعته چند قد باشه چهارشنبه؟ ببخشید دکتر.
حالا همین ساعت هم میتونه باشه. اگر کسی مشکلی
پنج شما میشه 4:30 ما.
4:30 شما نه؟ حالا همون
5 شما میشه 4:30 ما.
همین ساعت بذاریم، اگر خواست عوض بشه به من بگید. کسی مخالف
باشه. هي الساعة 4:30 إن شاء الله، 5 طهران 4:30 إحنا.
5 تهران 4:30
ها هي.
تمام.
ممنون دکتر، دستتون در نکنه. خداحافظ، به سلامت.
بيد الله. شكرا، ممنون. بيد الله.
ايه الساعة زينب اليوم الأربعاء المحاضرة؟
الساعة 4:30.
هذا الساعة.
السلام عليكم.
عليكم السلام أستاذ.
كان عندي مشكلة بالإيميل، أصلي يلا دخل المحاضرة.
خلصنا المحاضرة. يا أهلا أستاذ.
بلا أهم شيء يعني على مود الحضور مو غير شيء.
إيه ها.
فقط بهشون هم بگید که کلاسشون رو سیستم وادانای دانشگاه هم میتونن